Okay, so let's take off from where we left last time. And you remember that what we were doing, we were really trying to understand estimating the bias of a coin. So this is really, although there are lots of applications in randomized algorithms, it's also, basically some version of statistical hypothesis testing. We started off with population estimation, and a lot of it boiled down to, I have a coin whose heads probability is P, and I'm trying to estimate P. Right? I have a coin whose heads probability is P, I'm trying to estimate P. So I just do multiple independent flips of that coin. When I do S flips, the distribution is just a binomial. And so what I have is, when I fix my P and I let S go to infinity, it looks like a normal distribution. Formally, we can quantify this using the Houghton bound. And what we also showed was that, if you want an additive estimate of alpha, you cannot beat 1 over alpha squared in the worst case, meaning that if P is a half and you want an additive alpha estimate, you cannot beat 1 over alpha squared. Except there are certain situations where you can beat the 1 over alpha squared. And I just sort of wrote this theorem at the very end. And so let me just focus this a little bit more. Okay, there, much better. So fix an alpha. Remember, alpha is like the error that you want. Fix a delta. Delta is the confidence. And we're trying to understand what can you get with 1 over alpha samples. So it's inverse linear. What we can show is that if P is greater than alpha, so the probability is actually greater than alpha, then one can estimate P up to a constant multiplicative factor with probability at least 1 minus delta using a sample size. So the number of flips, that's S, will be O of 1 over alpha with this log 1 over delta, to boost your confidence. And specifically what I will show is that the probability that you get an estimate which is off by a factor of 2. Right? So with high probability, with this probability, we'll get an estimate that's off by a factor of 2. And you can usually trade this factor of 2 off with the constant over there. And note that when P is actually theta of alpha, then the estimate is also an additive alpha estimate, right? If you work the math out over here. So you can get an additive alpha estimate to P in 1 over alpha samples, but this is only possible, or this is possible when P is theta of alpha. And what I'm going to show you is the proof of this statement, and this uses something called the multiplicative Chernoff bound. The multiplicative Chernoff bound is one of the most important tools in the analysis of randomized algorithms, and this is one way of sort of introducing you to that tool. Okay, so let's continue. And let me first tell you what the multiplicative Chernoff bound is. So it's sort of it's a sharper version of Houghton for certain settings. So the multiplicative Chernoff bound. Okay, so we're in the same setting as before. We'll say xi's are in 0, 1. They're independent, but not necessarily identical. Right? So I don't need IID, I just need independence. And my random variable is xi, I going from 1 to n. Right? So these are the random variables. And I'm looking at the sum. So the multiplicative Chernoff bound basically has two versions. There's an upper tail bound and a lower tail bound. So what we get is that, so now the probability, so for now, let me just set epsilon to be in 0, 1. Although in general, in some of these bounds you can set it to be something more, and you'll see why that makes sense. The probability that x is greater than 1 plus epsilon times the expectation of x. So now you measure the deviation, unlike Hoeffding, where you measure the deviation additively. In Chernoff, and that's why it's called multiplicative Chernoff, you measure the deviation multiplicatively. This is less than basically e to the minus epsilon square the expectation divided by 3. So this is the upper tail bound, and the lower tail bound is this minus epsilon square expectation of x divided by 2. Now obviously for this lower tail bound it does not make sense to have epsilon being more than 1. That would be absurd. On the other hand, for the upper tail bound you could ask for epsilon being more than 1, and you do get bounds when epsilon is more than 1, but it is most convenient to represent in this form. Later on, if we come to applications where we need epsilon to be greater than 1, there's a more convenient form of the bound that can be used. So one doesn't use this directly. So this is the upper tail. This is the lower tail bound. Now I want you to contrast this. So these are the multiplicative Chernoff bounds. Just to contrast, I'm going to write out the Hoeffding bound over here so you can see the difference. So this is Hoeffding. So Hoeffding was of this form. It said x minus the expectation of x is greater than t, and this was less than 2 exponential minus t squared divided by n. Now what you get over here is some dependence on n. What you get here is just a dependence on the expectation. And this, so for example, there could be situations where even though you have n random variables, the expectation is much smaller than n. And in that situation, this bound is actually not going to give you much, but the multiplicative Chernoff bound is going to give you quite a bit. Now, I am not going to prove this. And actually, there was a point of confusion, I think, at the last lecture, where when I gave this example of the central limit theorem and the Gaussian, and I said how the mathematics of this conforms to the Gaussian, I want to stress that I did not provide a proof. I was just giving you intuition as to if this was a Gaussian, what you would expect, and show you that the Hoeffding bound gives you exactly what you would expect if x was Gaussian. Okay, so that was not a proof, and therefore, people are rightly asking, oh, but the central limit theorem only says something in the limit. How can you use that to argue something about a specific random variable? And one would have to quantify that. That requires a proof. So I'm only using that to give you intuition. But I think that intuition, that rule of thumb, is really important. And so I would like to show you why this bound conforms to x being Gaussian. This is not a proof. This is only explaining why this math makes sense and why the square over there is going to appear naturally. Excuse me. Okay, so remember, suppose, and again, this is just to understand the behavior of this bound. Suppose x was truly a Gaussian. So let's compute what is the variance of x. Now, because all the xi's are independent, this is just the sum of the variances of the xi's. Now remember, each xi is a Bernoulli. So each xi, let's say, has probability pi. So this is a Bernoulli, and let's just say that pi is the probability that xi is equal to 1, right? So let's just call that pi. So if you simply write out the formula for the variance, you get I going from 1 to n of pi minus pi squared. Now, sort of trivially, I'm just going to bound that by pi. And this, as you can see, is exactly the expectation of x. So the variance is at most the expectation, meaning that the standard deviation is at most the square root of the expectation. Okay? So what this means is that a deviation of epsilon times the expectation, which is what is being bounded over here. You're bounding the deviation being less, or you're saying what is the probability the deviation is more than epsilon times the expectation. So this, a deviation, let's write this in terms of how many standard deviations it is. A deviation of this is going to be at least epsilon times root epsilon x. That's the number of standard deviations. So this is sort of the k standard deviations times the root of the expectation. Okay, so I could just, this is an equality, and this is greater than equal to epsilon times root epsilon x times the standard deviation. Right? So a deviation of epsilon times the expectation in this case is basically a deviation of at least epsilon times root of the expectation standard deviation. So that's how many standard deviations. And so again, using this rule of thumb of what a Gaussian looks like, you know that the probability of the deviation is at most e to the minus k square, where this is k, and so this gives you e epsilon square expectation.
Could you move it up a little bit?
There. Right? So the probability of the deviation is e to the minus epsilon square expectation, and this is exactly what the Chernoff bound gives you up to some constant. So up to constants, this sort of rough rule of thumb gives you the bound. This is not a proof. This is just to explain why this bound conforms to x just being distributed like a Gaussian. Okay? So is this point clear? Okay? Now this tool, the multiplicative Chernoff bound, is incredibly useful. And so what I'm going to do now is I'm going to prove, that theorem about this estimating with 1 over alpha using it's a direct application of the multiplicative Chernoff bound. But after that, I'm going to do a series of applications of the multiplicative Chernoff bound, starting with actually some sort of concentration behavior of quicksort, a sort of quick and dirty proof. But you'll see that just using this, just using random variables that are between 0 and 1, you can do a lot. You can analyze lots of algorithms. Okay. All right. So now let me make this, and let me go back to the statement that I initially had, and that was let me go back and show you that statement. So I have p being greater than or equal to alpha. I want to estimate p up to a constant multiplicative factor using the sample size. Let's just apply the multiplicative Chernoff bound and see what we get. So I'm going to write the proof of the estimation theorem, not the proof of the Chernoff bound. Not the proof of the Chernoff bound. So again, and again, I want you'll see the usual game that we play here. We'll say xi is the indicator for the ith coin toss being heads, right? So that will be our. Sorry, let me just pull up the windows here. Okay. So, and remember that the way we do our estimate or empirical estimate. So the estimate for P is simply going to be the summation of xi, I going from 1 to s, divided by s, which is the empirical fraction that were heads. And so we're just going to use this as our estimate. So we need to analyze this random variable here. So we look at capital X being summation of xi, I going from 1 to s. And this is now exactly the setting for the Chernoff bound. So the expectation of x by linearity of expectation is just s times p. Right, so that is the expectation. So now let's apply the multiplicative Chernoff bound. So note that I have two bounds, one for the upper tail, one for the lower tail. So what I get over here is I'll say the probability that x is greater than 2 times the expectation. So I can set epsilon to be essentially 1. So I'll set my epsilon to be 1. So this is the probability that I get 1 plus 1 times the expectation. And so what is this? This is e to the minus epsilon squared. So epsilon is just 1. The expectation divided by 3, right? And what is the expectation? This is minus SP divided by 3. So essentially, as long as S times P is log 1 over alpha, I'm in good shape. And that's exactly what I'm going to get. So let me continue the proof over here. So I'm going to sort of see if I can keep part of this visible here. Okay. Okay, so remember, so I'm going to suppose I set my S. My S was 3 times the natural log of 2 over delta divided by alpha, right? So this is basically, this is O of log 1 over delta divided by alpha. If I set S to be this, then SP divided by 3 is equal to the natural log of 2 divided by delta, and therefore I get the probability of x deviating more than 2 times the expectation is at most delta over 2. Right? I plug this in. So S times P divided by 3 is the natural log of 2 divided by delta. Plugging that in over there, I get this being less than delta divided by 2. Okay? And now the probability that x is less than half of epsilon x. Again, this is an exercise, so we'll say as long as, well, keep this equal here. You can again get that this is going to be less than delta divided by 2. That's an exercise. You will set epsilon to be a half over here. So you set epsilon to be a half, and you might need a larger constant there because you'll get an epsilon squared divided by 2. So the S that you need over there will be basically 8 at an n. But in any case, you could, make that an 8 over there. And so you know that this is going to be greater than that. And so you will get this bound here. You can get the probability of the lower tail. And I will leave that as an exercise for the scribe to work out. So you get the probability of the upper tail, the probability of the lower tail. Now we're going to use another very important tool, a very simple tool. We'll use something called the union bound. So what the union bound says, Just going to write this out separately. The union bound just says the probability of a union of some collection of events is at most the sum of the probabilities. It's a very trivial bound, but very useful. So what it says is, if I have a collection of bad events, and I want the probability of the union of events, this is at most the sum of the probabilities. So I'm going to apply the union bound over here, and then what I get is the probability that x is greater than 2 times the expectation. I'm sorry, this should be 2 times the expectation, or x is less than half of the expectation is at most delta, just by summing these probabilities. In other words, the probability that x is in the expectation divided by 2 and 2 times the expectation, this probability is at least 1 minus delta. And what was our estimate? Remember, our estimate for P is exactly x divided by s, and the expectation of x is s times p. So you just divide this by p, and you get that this is essentially equivalent to saying that the probability that the estimate is between, just by dividing all of this by s, so you just divide all of this by s, the probability that the estimate is s divided by 2 and 2 divided by s, the probability that it is in that range is at least 1 minus delta. That's the end of the proof. And so what this says is that if you set s to be basically with s being O of log 2 divided by delta divided by alpha. So s is essentially inverse linear in 1 over alpha. You can get a multiplicative estimate, right? So you can get a multiplicative estimate. Now the multiplicative estimate tends to be weaker when p is larger. When p is close to a half, a multiplicative estimate is not as useful. But when p is very close to alpha, the multiplicative estimate is of use. So any questions about that? Okay. Yeah.
Sesh?
Yeah.
Yeah. So about the Chernoff bound itself, is this a loose one because it's not symmetric, and I see that it's maybe because of 1 plus epsilon and 1 instead of 1 by 1 plus epsilon, you have 1 minus epsilon. But typically epsilon is small, right? So they should be pretty close.
Well, I mean, the thing is, there is a difference in the constant there.
Yeah.
And also, actually, it turns out that the two tails are not necessarily symmetric. So the asymmetry in the upper tail and the lower tail is actually okay. So let me write something out which might explain that even more. But the asymmetry that you observe, in some sense, is inherent. It's inherent to the fact that when the expectation is actually kind of small, lower deviations are actually somewhat likely. But deviations that are very, so the lower tail and the upper tail do behave differently.
Okay. Okay.
Any other questions? Okay. Now
just because
yes.
the variables can't go below 0, and so if the expectation is small, then the total amount of place that you have to put the probability mass below the expectation is smaller?
Yeah, I mean, in some sense, you mean, are you sort of asking a follow-up to the previous discussion?
Yeah.
Yeah, exactly. The fact is, because this is a non-negative random variable. So let me just explain the connection to the Poisson distribution, and maybe that will give some clarity as to what's going on. Okay.
Okay.
Okay. So really, let's go back to thinking about BSP. And you say if you fix P and you let S go to infinity, this is a normal distribution. Sort of in the limit. Like, that's the way to think about it. So what's going to happen is your expectation is something like S times P. And this is really far out. Like, as S goes to infinity, this goes to infinity, you start seeing something that looks like that. But suppose you're looking at BSP, where P is like lambda over S, and now S goes to infinity. So it's like the probability of the heads is going down. So I'm looking at the limit of this process, this distribution. And this is basically a Poisson. So note that even as S goes to infinity, the expectation is fixed at lambda. And so what you have here is something that looks like that. And this typically is your lambda. So the situation that we are looking at over here, and the situation here, where P is roughly alpha, and the number of samples is like 1 over alpha. And think of sort of alpha going to infinity. What you're really getting is a Poisson tail. So this is a Poisson distribution, and therefore its behavior sort of is not as symmetric. And so what you do by setting is the lambdas are sort of like log 1 over delta, and that pushes things out a bit, but the upper and lower tails do have a difference. So hopefully that gives you more clarity. In general, one can go deeper and deeper into this topic, and it is a very interesting topic, lots of interesting connections to information theory and like functional analysis. But for the purposes of analysis of randomized algorithms, we don't necessarily need to go so deeply into it. All we need to know is basically the form of the multiplicative Chernoff bound, because we will be applying that in various settings. And again, just to sort of complete this discussion, so we had this sort of 1 over alpha squared, and we had this 1 over alpha bound, and you can ask, is there some sort of clean, is there an interpolation between these bounds? And there is something called the Chernoff-Stein theorem, or I guess it might even be called the formula. And this comes up in hypothesis testing, and this is really saying something about its sharper tail bounds for the binomial distribution, which kind of interpolate between these situations much more clearly. It is not as convenient to use in most of the applications that we have. So you can derive the multiplicative Chernoff bound, well, multiplicative Chernoff bound for IID trials from the Chernoff-Stein theorem. But it is, it tends to be a little clunky to use. There's connections to it. Expresses things in terms of, it uses like the KL divergence to express deviation probabilities. So for now, it suffices to have the multiplicative Chernoff bound and the Hufting bound. I will mention there is also something known as the Bernstein inequality, which is a more general form. Bernstein is a more general form of the multiplicative Chernoff bound and Hufting. And so you can see that here you have an additive deviation, here you have a multiplicative deviation, and Bernstein gives you something more general where you can kind of combine all these forms together. Again, in many applications, the multiplicative Chernoff bound in this form actually suffices to do an incredible amount of stuff. So I will not get into these other inequalities unless we come to applications where we need them. Okay, so with that, what I would like to do now is, again, just as a very nice application of the multiplicative Chernoff bound, I'm going to give you an important tool. So one can view it either as a statistical application or an algorithmic tool. and it's called boosting probability of successes. So a statistical, you can think of it as a statistical application or a boosting tool for the probability for success probabilities. Okay, so let me phrase this in somewhat more general language, and then we'll see specifics of it. So consider some distribution D, and so we can either think of this as discrete or not, but let's just say, let's think of it as discrete, or if continuous, then well behaved. Then I want to think of this then well behaved. Like, I don't want to think of crazy analysis type constructs. Just think of some well behaved distribution, and let F denote the CDF. Right, this is a cumulative distribution function. So I'm going to draw out the CDF here. And so the CDF might look something like this, where that's 1, right? And so what is the median? The median is F inverse of a half. So you look at half, and right there, that's the median. How to approximate the median? So how do you approximate the median? Well, again, we can do sort of the obvious thing. Take S samples and output the median of the samples, which one would call the empirical median. And it's natural to ask, how well does the empirical median approximate the median? Or to flip it around, what should you set S to be to get an accurate approximation of the median? Now you have to be a little careful here, because I'm not really assuming anything about the distribution other than, let's just say, some basic continuity. So this thing could shoot up like that, in which case getting the median exactly might be a little hard, because even if you're a little off, you could be far from the median. So one needs to sort of parameterize things properly here. So let me give you the main theorem at this point. So is the question clear? You're just trying to estimate the median of a distribution. You're going to take a bunch of samples. You look at the median that you get, and you say, okay, how far is this? Like, what can I say about the empirical median? Okay. So the theorem, and again, this is going to be a direct application of the multiplicative Chernoff bound, is, for epsilon delta being greater than 0, maybe we'll say less than 1, one can output a value, or rather, let me just say that even better, let me just say the empirical median. The empirical median lies basically between, is approximately the midpoint, with probability at least 1 minus delta, using, again, we'll see sort of our favorite expression coming up, the log 1 over delta divided by epsilon square samples. So going back to our picture here, what I'm saying is, Okay, so let me sort of blow that picture up over here. Right, so this is half, and this is the point that I'm getting. So here's my CDF. So what I'm saying is, well, go to half minus epsilon and half plus epsilon, and look at the corresponding points, F inverse of half minus epsilon, F inverse of half plus epsilon, and you will output a value in that range, in this range here. So you can get as close to the median over here. Now note that the half minus epsilon, half plus epsilon might represent a much further range depending on the steepness of your distribution, right? But what it says is, if you want to get up to epsilon in terms of the probability mass, so you want to get F inverse of half minus epsilon to F inverse of half plus epsilon, you can do this with essentially 1 over epsilon squared samples. So is the theorem clear? Any questions about the theorem? Okay, if not, let me now proceed with the proof. Okay, so now I'm going to define, remember I took S samples, and define x1 to xs. Again, these are going to be independent Bernoullis, independent, in this case identical Bernoullis, where xi is the indicator for the ith sample being strictly smaller than F inverse of half minus epsilon. So go back to my, let me sort of zoom out a bit. So I claim that things are going to lie in this range with high probability. So I'm asking, the bad event is, what's the probability that my sample lies in here? Now what's the probability that I get a sample in here? Okay. So what is the expected value of xi, which is basically just the probability that xi is 1? What is the probability that my sample is going to lie less than that? Any thoughts, any guesses?
Well, the CDF, like the CDF evaluated at the lower point is going to be the probability, like that x is less than that, right?
Yeah. So what is the probability?
So what is the just f of 1/2 minus epsilon? No.
Almost.
I guess it's just 1/2 minus epsilon.
It's just 1/2 minus epsilon. That's the probability of lying in this range. That's half minus epsilon, right? That's exactly the definition of this. Just to be formally correct, I'm just going to say it's less than equal to half minus epsilon, because if the distribution was discrete, then I could get some inequality here. Okay, so if it was continuous, then this would be an equality. But if it's discrete, then this is an inequality. So the expectation is less than half minus epsilon. Okay, so what is the expectation of the summation of xi's, I going from 1 to s? This is s times half minus epsilon. Okay, so again, let me call this capital X. Okay, now what is the probability that x, let me now apply the multiplicative Chernoff bound, that x is greater than that 1 plus epsilon times the expectation, and this is just sort of plugging in the bounds as is epsilon square times the expectation divided by 3. Okay, now I'm not going to work out You saw the settings of the math and how these things work, so I'm not going to work out this calculation right here, but basically if the expectation of x, if I set s to be omega of log 1 over delta divided by epsilon square, then by plugging this in, I can ensure that this probability is at most delta divided by 2, right? And that's because the expectation of x is basically s divided by 2. And by setting s to be at least log 1 over delta divided by epsilon square, I can get this to work. So for the scribe, please work that out exactly. But for all of you, this is a good exercise to work this out. This is sort of the typical Chernoff bound calculation that you'll get. Okay, so with probability delta over 2 at most, I get, now what is x? X is the number of samples that are significantly less than the median, right? So let me write this down. So write it down over here. So x is equal to the number of samples, x is equal to the number of samples that are less than this quantity, right? That is significantly less than the median. To sort of to show you that picture again, right? So here's half minus epsilon, and this is half plus epsilon, right? So I'm looking at how many values fall in this range over here, and this is x. X is the number of samples that fall in that range. And we just show that the probability that x is more than 1 plus epsilon times the expectation of x is less than delta over 2. Okay, now let me start plugging in some values here. 1 plus epsilon, the expectation of x, this is s times half minus epsilon. Okay, so let me work this out. Let's work this out in some detail. So we get s times half. I get a half epsilon minus epsilon, so I'll get minus epsilon over 2 minus epsilon squared. And note that this is actually strictly less than s over 2. So what this means is that the probability that x is going to be greater than or equal to s over 2 is certainly less than the probability that x is going to be greater than s times half minus epsilon over 2 minus epsilon squared, right? Obviously, the probability of this event is going to be less than the probability of this event, right? Because this event is contained in this event. And this is exactly equal to the probability that x is greater than 1 plus epsilon times the expectation being at most. So this is probability of x being greater than s over 2 is at most delta over 2. What does this mean? What does that mean with regard to the median?
Well, if x is larger than s over 2, then the median will fall inside
this region. Exactly. So what we know is that the probability of x being less than s over 2 is at least 1 minus delta over 2, which means the probability that the median is greater than f to the minus. So the probability the median is greater than that is at least 1 minus delta over 2. So this is the good event. So what this is saying is that with high probability, your median is going to be outside this region, which means your median is going to lie somewhere in here. Now, by an analogous argument, you'll have to work this out. This is again for the scribe, so an exercise here. The probability that the median is less than f inverse of half plus epsilon is again going to have the same behavior using a multiplicative Chernoff bound. In this case, instead of an upper tail bound that you used here, you'll use a lower tail bound, but you'll argue that you cannot have too many elements, with high probability, or let me say this differently, the probability that there are S over 2 samples that fall in this region is again going to be small. And so the probability that the median is less than this is going to be at least 1 minus delta over 2. You do a union bound, and what you get is the probability that the median is in the range f minus half minus epsilon f inverse half plus epsilon is at least 1 minus delta. So the median basically is accurate, or according to this. And the median falls into the right interval. Okay? Any questions about that? Right, so this is saying that this is why the median has, is essentially has some sort of constant. The mean will not have such properties, but the median will. So you can get as close to the median sort of as you want. Questions? Okay. So now, as an exercise, you can show that for p less than half, f inverse of p. So this is some other point on the CDF, and this can be approximated really in the same vein. By approximated, I mean approximated as you can get something between f inverse p minus epsilon and f inverse p plus epsilon using... Does anyone have a guess as to what this expression should be? How many samples do you need? So by approximated, I mean you get something in f inverse p minus epsilon, f inverse p plus epsilon. What do you think the right... What is the expression that you expect? Basically using Chernoff bounds. And thoughts?
Well, it has to be related to p.
Exactly.
Because we're essentially replacing the 1/2 with p.
Exactly. So it's related to p, which makes sense, right? Because if p is small, you're probably going to need more samples. Okay, so I'll write this out. You get epsilon squared times p. Interestingly, you need 1 over p, because if you're trying to detect an event whose probability is at most p, which is the probability of getting a sample less than this, you need at least 1 over p. And so it says 1 over p with the additional log 1 over delta epsilon divided by epsilon square factors gives you essentially enough concentration for things to work out. Okay? Now, with the median approximation, we have an important boosting tool. I'm going to describe this process, and over the next few days, we will do a number of, we will actually, I'll give you a number of results where this is used, and so the application will become clearer. But right now, let me sort of describe it so that, just to warm you up to how this is used for boosting probabilities. So, often we wish to compute some quantity that I'll call Q, right? Min-cut values, whatever have you. You're trying to compute something. Usually what you want is, it's okay to get some approximation with some approximation. So we can phrase this as we wish to compute some value in an interval I. So you have some interval I and you want to compute values in there. Actually, the median is an example exactly of that. This is your interval and you want to compute some value in that interval. You're trying to find a value in that interval. And often what you will see in randomized algorithms texts, or even more so in papers, we will describe a random variable x such that x lies in the interval with probability at least 2/3. So we're just going to suppose all you did was you were able to describe a random variable x such that x lay in that interval with probability 2/3. And then you'll see that most of the papers will say, I'm done now. And you might say, but you only got it with probability 2/3. What you really want is to be able to get it with any sort of with arbitrarily high probability. So you want to say, if I wanted 1 minus delta probability, how am I going to do that? Well, you simply use the median trick. So now we know that the median, so what this means is basically the way that you'll boost the probability. The boosting of the probability is done by compute O of log 1 over delta independent samples of x and output the median. And the median will be in the interval. The median will be in the interval with probably at least 1 minus delta. This is the boosting. The boosting step will often not be described explicitly. It's kind of assumed that once you do this, you can immediately do that with just an extra multiplicative cost of log 1 over delta. So if you don't care about constant factors, then once you get to probably 2/3, you're done. You can replace this with half plus epsilon for any constant epsilon. What this means is henceforth, we are not going to carry around the dependence on delta any longer. We will just get things with probability 2/3, and then you can apply the median. And this I like to call, or is sometimes referred to as the median trick. And henceforth, what I will do is I will compute random variables, then I'll say use the median trick to boost probability. Indeed, as long as you get more than 2/3, you're done. Now you need to get something that is better than a half for the median trick to work. But as long as you get something strictly greater than half by a constant, then you can apply the median trick to boost your confidence. So this is boosting the confidence. And it's important that you just pay a log 1 over delta, and this is fairly cheap. Okay, so at this point, I'm going to pause for about 5 minutes, and I'll take questions. And then, once we're done with the questions, we'll come back and I will then talk about the analysis of Quicksort. So let me, I just want to sort of clarify that point. I think I had misspoken earlier when I said when the CDF is steep, then actually your approximation is quite precise, because this interval ends up mapping to a smaller interval on the x-axis. If your CDF is not so steep, is actually very gently increasing, then this approximation here will actually, this interval here will be a much larger interval. Typically, if your distribution is discrete, then your CDF will have these jumps as step functions, and your approximations will be accurate. Right? When things are steep, it's much better. Okay. So now let's go back to randomized quicksort, where I promised that I would explain why randomized quicksort has an n log n probability, has an n log n running time with extremely high probability. So randomized quicksort. Now, the theorem that I'm going to give you is not the sharpest. I'm not going to optimize constants. The aim is really to demonstrate the power of the Chernoff bound. The fact that, just using this simple version of the Chernoff bound, you can show behavior about fairly complex procedures like randomized quicksort. So let me first write out the theorem, and then we can discuss it, and then I will show you the proof. So the theorem is for any k greater than 1, the number of comparisons made by RQ sort, that's randomized quicksort, is less than, I'll say, the constant that I have is 16k n log base 2n. Actually, no, my apologies. I'll say 16k n natural log of n with probability at least, this is going to be extremely, so I'm going to get something better than what I'm writing here, but I'm just writing this to give you the cleanest form, n to the k minus 1. So what I'm saying is that the number of quick comparisons made by randomized quicksort is going to be less than 16k n times natural log of n with probability 1 minus essentially n to the minus k. Now I want you to contrast this with Markov, where Markov would basically say something like that. This is what Markov would give you. And even with Chebyshev, you will get something better than this, but you will not get behavior that decays exponentially in k. Right? So this is giving exponential. This is not the sharpest theorem one can get, and actually this is pretty weak because this constant here 16 is quite large. And you can get better constants by sort of even tweaking with the proof that I have. And I chose these constants just to make it easier to present and show how you would use the Chernoff bound. Are there any questions about this statement? Does this make sense? Okay. So let's do the proof. Now I'm going to, instead, you remember that when we discussed the expectation, I defined these Bernoullis, which were denoting the event that the ith element and the jth element were compared. I'm now going to use a different set of random variables. So remember that A is my array here, And remember that B was the sorted version. Now, although you'll see that it's not going to be particularly important for me, I'm just recalling the notation that I used. So let xi be the depth of the element a of I. And let me tell you what I mean by depth. So construct the tree of pivots. Right? So what does that mean? Remember, I started with A and I picked some pivot. So I'm going to, let's say that pivot, let's just say what happened to be, the 15th element. So I can say that was the pivot. Then everything less than the pivot would go into this call. Everything greater than the pivot goes into that call. Over here in the call that was less than the pivot, there was some pivot that was chosen. So some pivot goes there and then it would fork, and some pivot goes there and it would fork until this goes all the way down until your array basically, this is now a size 1 array. Size 1 array, which is your base case call. So this is the tree of pivots. Now all nodes are compared with the ancestors. Right? Because if you have some node that became a pivot here, this must have been compared with that while deciding that this node has to go on the left side. It has to be compared with that, so on and so forth. But it will not be compared with anything else. So I'll say all nodes are only compared with their ancestors. Okay, is that clear? So all nodes are compared with only their ancestors. This means that the number of comparisons can be expressed as the summation of xi, I going from 1 to n. Okay? What I'm going to prove is actually a much stronger theorem than just this. I'm actually going to prove to you that the recursion depth is at most going to be 16k log n. And you'll see how you'll see that. I'm going to prove that I'm actually going to bound the recursion depth. Okay, so does this make sense? The number of comparisons is basically the summation I going from 1 to n of xi, of the depths of the trees. Question? Okay. Okay.
Professor?
Yes.
When you say you bound the recursion depth, we still technically keep like an O and log n because we're just adding smaller values to that to get the total number of comparisons?
You mean this?
Yeah, because so that's like the sum of all the depths of each of the nodes, right?
Sum of all the depths of every node.
Of every node.
Not just the
So
leaves.
How does that relate to the recursion depth?
So you'll see that the maximum value of xi is the recursion depth.
Oh, okay. Got it.
So I'm just going to actually show you that the maximum xi is going to be small.
All right, thank you.
Okay? All right. So now let's look at the following question. What is the probability that xi is greater than equal to 16k natural log of n? Let's just try to understand what is the probability that some node is going to have a depth much larger than essentially some constant times log n. Again, I'm not optimizing the constant, just to demonstrate the proof techniques for you. Okay? So let's follow the sequence of recursive calls of the arrays containing this element a of I. Right, so this element a of I, so somewhere here, there's going to be a sequence of recursive calls that contains this element. And then at some point, this element becomes the pivot. And when it becomes the pivot, then that's it. Its depth is decided. Okay? Denote this sequence by A1, A2, going all the way up to A of D, where now D is the depth. Right? So this is basically xi. I just don't want to call it A of x of I, you know, just so it's A sub D. This is the eventual value of xi. Right? So what happens is, again, if you go back to this tree, let's go back to this tree, there's an array over here, and this is the array A. There are smaller and smaller subarrays here. So I could look at my element A of I, could say, oh, okay, it's here. My element is over here. Then my element ended up here, so on and so forth. And I can trace this path down. This I'm going to call A1, A2, A3, A4, so on and so forth. Right? And this is the sequence. Okay, any questions here? So note that A2 is a child of A1, A3 is a child of A2, so on and so forth. Right? So AI plus 1 is a child, I'll say technically a child call of A sub I. Okay? Now at every call, a pivot is chosen. So at every call, a pivot is chosen. And I'll say the pivot is balanced if A, so let me not use I, let me use J instead, because I used I for the element. If AJ plus 1, the size of AJ plus 1 divided by the size of AJ is at most 2/3. So as I go down this tree, as I go down the tree, the arrays are shrinking. But maybe they're not shrinking fast enough. I call a pivot balanced if there was enough shrinkage, 2/3 shrinkage. Maybe balanced isn't the best word. I should maybe call it shrinking, but I'll say, no, let's just keep the word balanced over here. So pivot is balanced if the next call gave you an array which was at most 2/3 this array, and this is the call that contains your element I. So these are all random variables. These are all random variables. Okay? Now the probability that a pivot at AI is balanced is at least 1/3. Why? Let's look at AI over here. This is AI. Imagine sorting it. So sort AI and look at the middle 1/3 of the elements. Look at the middle third of the elements. If the pivot is chosen anywhere in here, then both sides of the call will have size at most 2/3. If the pivot is chosen anywhere in here, so you took AI, imagine sorting it, and look at the middle 1/3 of the array. If your pivot was in the middle 1/3, then the pivot is going to be balanced. Does that make sense? Okay. Now, for every balanced pivot, aj plus 1 drops by
Professor, the paper is off the
2/3. I'm sorry, okay. For every balanced pivot, the size has dropped by 2/3. Okay? So for every balanced pivot, the size has dropped by 2/3. Okay. So it's okay. So
Wait, how do we know that the size has dropped by 2/3?
from its previous, or I'll just say that for every balanced pivot at AJ, I should just say this. There. Right?
Oh, sure, yeah.
That's I just rewrote what I had.
Yeah, multiplicatively. Yeah.
Multiplicatively, it's dropped by a 2/3 factor. Okay? Alright. So, now remember, now again, like this analysis, I'm being very loose with the constants, so I keep saying over and over again. Okay, so now let me sort of write out the indicators that I'm going to be using. So let yi be the indicator, I'll say yj, for the pivot at aj. The pivot at aj being balanced, and we just argued that the expectation of yj is at least 2/3. Okay, so now and let's say y is the summation of yj, j going from 1 to, in this case, we are trying to understand what is the probability. So let's just say, what is the probability that
the expected value is greater than 1/3.
I'm sorry, the expected value is greater than 1/3. My apologies. Yes. So let me refer to this as D. So I'm saying, what is the probability that the depth was more than D? So you have some sequence, and eventually it goes to D, it potentially goes to something more than D. So, okay. So I go all the way up to D. So I look at the D calls that are there, because I'm looking at the probability there are more than D calls. Let me just look at the first D calls, where again D is 16k natural log of n. Okay. Now let me try to understand what is going on. The yj's are independent. So I can apply the Chernoff bound to y. So this is key, right? To discover what are the random variables that you can apply the Chernoff bound to. And I can apply the Chernoff bound to y. Before I apply the Chernoff bound, let me first sort of tell you what are the restrictions that I'm going to have on y. So suppose y, and just to, maybe I'll write this out, the expectation of y is at least d over 3. Suppose y was more than d over 6, right? So this is 16k natural log of n divided by 6. Suppose y was more than this. That means you have these many. This is the number of balanced splits. what this would mean is that this is at most 2/3 to the power 16k log n divided by 6. Right? And that's because for every balanced pivot, the size dropped by a 2/3 factor. If you had that many balanced pivots, if you had 16k log n divided by 6 balanced pivots, the size would be 2/3 to that power. Right? And let me just write this out as 2/3 16k divided by 6, the natural log of 2, that to the power. I just rewrote this. So take a calculator. You can verify that if k is greater than 1, then this, this is times n, which is the initial size. Then this quantity, when k is greater than 1, this quantity is less than a half. It's strictly smaller than a half. It's like when k is equal to 1, this thing is like 0.49 or something. Which means a of d is going to be less than 2 to the log n. It's going to be strictly smaller than this, which is 1. But this cannot happen because the depth was d. So AD has to be greater than 1 because as the calls went down, you know that there is a call. There cannot be, no AD can be more than 1. So this is important. This is important. I just said every balanced pivot is going to drop the size by 2/3. If you have too many balanced pivots, well, the size is then going to drop less than 1, which is absurd. So you cannot have too many balanced pivots. And so this is just sort of cranking out some math over some numbers here, saying that if you had more than d over 6, so this is d, if you had more than d over 6 balanced pivots, your size is going to be n times 2/3 to the number of balanced pivots. It's actually even smaller than that, but this is just an upper bound. And just reworking this is going to be less than a half. Like, you just have to plug in the numbers and check. So if k is greater than 1, this is less than half, which means that the size of AD is less than n divided by 2 to the log base 2 of n, which is 1, but this cannot happen. This is a contradiction. So you know that y has to be less than d over 6. That's the whole punchline of this argument. But the expected value of y is d over 3. Chernoff bound is now going to give you the concentration that you desire. Does this argument make sense? So let me pause here and take any questions on this. Okay.
I'm kind of confused exactly why we're trying this y is greater than or equal to d over 6.
Because what we're arguing with this is that y actually has to be small. We're arguing that y has to be small, but then the expected value of y is large, and y is a sum of indicators. Right? So y is the sum of indicators. And therefore, since y is the sum of indicators, the Chernoff bound applies to y, which means the probability of this the probability that y is going to be less than d over 6 is going to be so small, and this basically gives you the final bound that y, the probability of the running time being large is small.
I see.
So let me write out the next few steps and then maybe it'll become more clear. Okay? Okay, so now apply the Chernoff bound on y. So I'll just say the probability that y is greater than 1 minus half of the expected value of y is at most, so you plug in the bounds over there and you get minus expectation of y divided by 8. And what is the so the expectation of y was, I'm sorry, I'm messed up this bound. Probably the y is less than this. Sorry. So the expectation of y is at least 16k natural log of n divided by 3. And so you plug this in over here. You plug that over there. And you'll get that this is at most n to the minus k. It's even better. Like, I'm being loose over there, but it's at most n to the minus k. Okay? So the probability that y is less than this is, now you plug this in over here, so this is just saying the probability that y is less than half times 16k ln n divided by 3. Remember, so this was d, right? Is at most n to the minus k. So the probability that y is less than d over 6, which I can write as this form, is that. So the probability that y was less than d over 6. Now what was y? So this, okay, so let's sort of chain it all together. We're saying, let me sort of go back all the way. Let's look at xi. We're saying, what is the probability that xi is greater than d? For xi to be greater than d, this random variable y that I define has to be less than d over 6. But the probability that y is less than d over 6 is small. So when I put it all together, I get the probability that xi is greater than d is at most n to the minus k. So the probability that xi, the depth of I, is more than d, where d, again, sort of is 16k log n. So the probability that xi was greater than d is at most n to the minus k. Now this only argues something for xi, but then I can now do a union bound. So this is an extremely powerful method to break up the bad events into a collection of smaller bad events. So this is a bad event. The probability that the depth of I is large, that's a bad event. You're trying to argue about the union of these bad events. So the probability over the union of I that xi is greater than d is at most the sum over all I of the probability that xi is greater than d. So I is going from 1 to n, and this I can just bound by n to the minus k minus 1 by the union bound. Now what this means, writing out separately, is just saying that the probability that randomized quicksort has any call at depth 16k natural log of n.
Professor, the paper is off the
sorry. The probability that randomized quicksort has any call at depth greater than or equal to 16k log n is at most n to the minus k minus 1. So clearly the probability that randomized quicksort makes more, because if it made more than 16kn comparisons, if it made that many comparisons, then there has to be some call whose depth is at least 16k log n. So the probability that it makes less than these many comparisons is at most the probability that randomized quicksort has some call at depth at least 16k log n, and this probability is at most n to the minus k minus 1. And so then that completes the proof. Okay? So I have run out of time here. So let me just give you a quick 1-minute summary. After that I will stay and I can take any questions that you have. I wanted to prove that the number of comparisons made by randomized quicksort is at most 16k n natural log of n, with probability at least 1 minus n to the minus k minus 1. So I have this sort of exponentially decaying tail in k. There are stronger versions. I'm not optimizing the constant here. Now the way that I'm going to do this analysis is really I'm going to build the tree of pivots. I'm going to look at the depth of any element. And the number of comparisons is the sum of depths. Now, what is the probability that any given depth for a fixed element is more than 16k log n? The way I do this is by, as I go down the recursion tree, I track which of the pivots were balanced. And I say there is a reasonable chance that a pivot is balanced. There's a 1/3 chance that a pivot is balanced. Now, if I got many balanced pivots, then A sub d, the dth call in this depth, is going to be extremely small. The array corresponding to that will be too small, and that gives a contradiction. This means that this process could not have seen many balanced pivots. The number of balanced pivots seen was actually at most d over 6. But if the number of balanced pivots seen is so small, on the other hand, the expected number of balanced pivots seen is high, so you can apply the Chernoff bound to bound that deviation. And once you get that deviation, you get the probability that xi has a large depth is at most n to the minus k. This only gives you a bound for a specific I. So you do a union bound over all of them, over all the i's, over all the elements, and by the union bound, you basically get n to the minus k minus 1. And that completes the proof. One can get sharper proofs by using better versions of the Chernoff bound. Essentially, what I've assumed here is that when things are not balanced, there is no shrinkage, which is not true. Moreover, I've assumed that when things are when you get a balanced pivot, it only shrinks by 2/3, but that's also not true. You could get something better if you have, if the split was actually almost a half, then things shrink even more. So if one takes into account many of these many of these subtleties, one can sharpen the bounds here and get much better constants over there. On the other hand, this is a demonstration of how you use the multiplicative Chernoff bound with the union bound to sort of prove results. It's a very common technique. So I'll end here and I'll take questions.